that acts on the fluid elements here to affect their motion, despite the fact that there is a stress buildup. And I gave you an argument about that just in terms of looking at what these viscous forces ought to look like, and that the viscous force from this side on that particle will be equal and opposite to the viscous force from that side. You can see it mathematically in the following way. So I'm going to take this expression for the stress tensor that is built up as a result of the viscosity, the coefficient of viscosity eta. And the rate of change of the momentum of a fluid element per unit volume and per unit time, that's basically a force per unit volume that acts on a fluid element. And that force per unit volume is going to be delta T jk slash k, the divergence of the stress tensor. If you think through energy momentum conservation, this is the meaning of the divergence of the stress tensor. And so a simple example of this is that if you have a medium that has a homogeneous pressure, then each particle feels an equal pressure from all sides and doesn't feel any net force. But if there's a pressure gradient, as there is in this room or in a swimming pool, then that pressure gradient will produce some net force on the particle, say, or on a bubble in this room or a balloon that tries to push it up because there's a pressure gradient. The pressure increases downward. So it's the gradient of the pressure, or more generally, it's the divergence of the stress that produces this force per unit volume. And so we can just ask ourselves, for this stress tensor, what is the gradient? So we want to look at the gradient of the gravitational wave field itself, or the divergence, I mean, of the gravitational wave field itself. Now, I've assumed that eta is homogeneous throughout. This was a homogeneous medium, so I didn't have to differentiate eta. But let's remember that h is a function of t minus z, but its components are all x and y components. And so when you differentiate, you get a non-zero result only from differentiating in the z direction. But when you contract on this k has components only in the x and y directions, and so the divergence vanishes. It's because the directionality associated with the gravitational waves is entirely transverse. The propagation is longitudinal. In words, it's because the waves are transverse, and the very fact that the waves are transverse guarantees that this divergence vanishes. And so that divergence vanishes, and so in fact there is no net force acting on any fluid element, and that shows up pictorially in the argument I gave you about the forces that are exerted from the different sides on the fluid element. Yeah.
So just going back, you've written the fluid shear as a symmetrization of the divergence of the velocity. Yes, but so you only have one term down there. Is that because there's symmetry in the?
It's because the divergence of the velocity, when I computed it up here, was something that on the right-hand side was already symmetric.
Okay, so that's where you dropped your 2 then.
So that's where so there's this 1/2, but I dropped the 2 from.
You need another 2 when you add them together to get that 6.
Well, what you do is you take an average, and so sigma jk, I've lost it from here, but sigma jk is 1/2 vj slash k plus vk slash j, and then remove the trace. And so all this is doing an average, and when I compute the first term, I get something that's already symmetric. So when I do the average, the factor of 1/2 remains. Yeah. Yeah. So this factor of 1/2 remains down here. Okay, other questions? Okay. Okay, so having cleared up that last piece, that last issue about the case of the viscous fluid, let me talk now about an elastic medium. I claim once again, and for essentially the same reason, that in the case of an elastic medium, where these motions then, instead of producing these shearing motions, instead of producing a shear force, they just produce an elastic restoring force. But in that case, once again, and for the same reasons, there will be no net force acting on any fluid element. Each fluid element will continue to move inertially, because for the same reasons as before, the divergence of the stress tensor associated with the elastic restoring force vanishes, or the elastic restoring force from this side on that particle, which is trying to pull it forward, from that side on this particle is trying to pull it back. They counterbalance each other. So in the case of an elastic medium, once again, the particles move inertially. Here, by particle, I mean a particle of the elastic medium, rubber or whatever it may be. I don't mean particle in the sense of a fluid with these individual particles running around and producing viscosity. So call this a material element. A macroscopic material element. Each one moves inertially. Once again, we will have then a shearing, a rate of shear, sigma jk, which is going to be 1/2 hjk transverse traceless with one time derivative for the rate of shear. But for elasticity, the thing that you resist against is not the rate of relative motion of these fluid elements, but actually just their displacement, which is the time integral of the rate of shear. That's the thing you resist is any relative displacement. Just move a little bit and hold it, and there's a restoring force trying to push back. And so this shear, as opposed to the rate of shear, is the time integral of the rate of shear. And so it is 1/2 hjk transverse traceless with no time derivatives on it. And this is the thing to which there is resistance. And that resistance is described by then a stress tensor perturbation, which is equal to -2 times the coefficient of elasticity, of shear elasticity, 2 mu times sigma jk. Just to comment, the factor 2 here and the factor 2 in the shear case, wherever I wrote it down, I've thrown it away. In the shear case, there's a similar factor 2. Those are historical because in the present era, we work with different fundamental quantities than people did in the 19th century, and these are 19th century concepts. And so the notation and the language have changed, but we have kept the numerical coefficients so that the numerical values that you will look up in a 19th century textbook for the coefficient of elasticity are the same as you would look up in a 21st century textbook. So the 2 is of historical origin. So the stress tensor then, you develop a stress in response to this shear of the shape of the material. And that shear is given by this expression, and so this is equal to minus then mu hjk transverse traceless. And that means then that the Einstein field equations, which take the form of this wave equation for the gravitational wave field, are equal to that minus sign cancels this minus sign, and you have plus 16 pi mu times hjk transverse traceless without any time derivatives on it. Of course, since the waves are propagating in the z direction, we have minus dt squared plus dz squared acting on hjk transverse traceless is 16 pi mu hjk transverse traceless. Okay. Now let's suppose that these waves are monochromatic. They have a frequency omega and a wave number k. K is just 1 over the reduced wavelength. That is, it's 2 pi divided by the wavelength. That means that hjk transverse traceless is some function of omega t minus kz. Or let me write it as it goes as e to the I kz minus omega t using the usual complex notation. You take the real part. Okay. So I can just feed this back into that wave equation where the influence of the elastic medium is on the right-hand side. And when I feed it back in, this minus dt squared will give me an I omega squared with a minus sign. The plus dz squared will give me an ik squared times the h is 16 pi mu times the h. And so this gives me what we call a dispersion relation, a relationship between the frequency and the wave number for these monochromatic waves that says omega squared, because I squared is minus 1, minus k squared is 16 pi mu. So that is the relationship between their frequency and their wave number. Now, I am going to claim that this is a very tiny correction, that the effect, as we will see, and so I want to solve for omega explicitly in terms of k. Let me just do it up here. Then omega is, using the fact that this is small, omega is equal to k squared plus 16 pi mu square root. I factor the k out times square root of 1 plus 16 pi mu over k squared. And then I expand this by the binomial expansion, or power series expansion. That's k times 1 plus 1/2 16 pi mu over k squared. Or omega is at first order, in this quantity I've claimed to be small, it's k plus 8 pi mu over k. So there's a piece that goes proportional to the wave number, that is 1 over reduced wavelength, and then a tiny piece that goes as the inverse of that. Okay. Now I want to remind you from your study of waves previously that the phase velocity with which these waves propagate is the ratio omega over k. And what the phase velocity means is you have these monochromatic waves, and you just look at the speed of the wave crests and troughs, and that's the phase velocity. You notice the phase velocity omega over k is equal to 1 plus 8 pi mu over k squared. And so I've claimed that this is going to be very small. That says the phase velocity is a little bit faster than the speed of light. But the group velocity is d omega dk. And what the group velocity means is if you superimpose waves of slightly different frequencies in order to build a wave packet, like you do in quantum mechanics, say. So you have some wave packet that has an envelope that looks like this, and the individual waves look like that. The velocity of the envelope is the group velocity. So this is a bit of mathematics or physics that most of you will have seen before, but I'm reminding you of. If you haven't seen it, you will see it in quantum mechanics classes, but you'll see it in classes, any class that deals with propagation of inhomogeneous waves, and with wave packets, you'll find that this is true. It's something it takes maybe 10 minutes to prove, and I don't want to take the 10 minutes. Okay, so the group velocity in this case is the derivative of omega with respect to k, and that's 1 minus 8 pi mu over k squared. And so these gravitational waves have an envelope that propagates at a little bit less than the speed of light, while the individual waves, oscillations inside there, propagate a little bit faster than the speed of light, moving from the back toward the front as the waves propagate. So I want to ask myself the following. Let's compare the arrival time, let's compare the propagation of this envelope with the speed of light. So I want to look at this difference in velocity, 1 minus v group, which is 8 pi mu over k squared, or it's 8 pi mu lambda bar squared. I want to look at that. And this is the speed of light, so let me write that as v light minus v group for the gravitational waves. And I want to ask then, by how much will this wave packet lag behind the light, or something propagating at precisely the speed of light, after the wave packet is propagated for this great big distance that's the radius of curvature of the universe, where again the curvature is produced by the elastic medium that is filling this model universe. Okay, so I want to take this quantity and I want to multiply it by the radius of curvature of the universe. And so I'll multiply this by radius of curvature of the universe and see then by how much there is a lag. Okay. So this amount of lag is going to depend on the size of the elasticity coefficient, mu. And so what I need to tell you then is that the speed of sound in this elastic medium is the square root of mu over rho. And since the speed of sound has got to be less than the speed of light, that says that mu is less than rho. So that means that this distance, this lag distance, let me call this distance that I'm computing the lag distance, L lag, in propagating basically around the universe, or over the Hubble distance, over the distance of the radius of curvature of background space-time. This lag distance then is going to be less than 8 pi rho lambda bar squared r. But 8 pi rho is 1 over r squared, the radius of curvature of the background space-time squared. So this is less than lambda bar times lambda bar over r. That's pretty small. What this says is that as this wave packet propagates, as it goes the full distance corresponding to the radius of curvature of space-time produced by the elastic medium, it's going to lag in distance propagated relative to propagation of the speed of light by an amount that is a small fraction of a reduced wavelength. So you imagine launching a gravitational wave through an elastic medium from here and letting it propagate for 10 to the 10 light years distance. And the gravitational wave has this wavelength. The amount by which a wave packet will lag due to dispersion, the word we use here is dispersion, that's propagating at less than the speed of light, is by something small compared to that wavelength, something very tiny amount. Yeah. So the lag distance is less than, this must be small compared to 1 in order for these even to be waves. So the lag distance is small compared to the reduced wavelength of the waves. So dispersion is totally negligible. So you begin to get a feeling for the fact that gravitational waves just don't interact with much of anything. And so let me finally, as my final example, try to build a medium that is the best absorber or scatterer or disperser of gravitational waves that I can find. Yeah.
Sorry, I have a question. Now, going back to where you said that 16 pi mu is negligible in comparison with k squared, or is much smaller than k squared, right? You made that assumption when you were calculating the approximate value of omega on the dot board.
Where are we?
In the bottom right corner.
The bottom right-hand corner. Yeah.
And you're making the assumption that...
Okay. So I'm claiming that this is small compared to 1. We now have recognized that mu, in fact, or 16 pi mu, or 1/2 times 16, let's take the 8 pi mu. 8 pi mu, let me put it in a different color. 8 pi mu, well, let me go back up here. 1/2 times 16 pi mu is less than rho, which is of order, or is less than 8 pi rho, which is of order 1 over r squared. And 1 over k squared is of order lambda bar squared, or it's equal to lambda bar squared. So this is lambda bar squared over r squared, which is the thing that has to be small compared to 1 in order for these to be waves. So thanks. That was oh no, I'm glad you asked that, because I made that assertion, but then I didn't demonstrate that it was all right in the end.
For some reason I accidentally flipped in my mind the r squared and the lambda squared, so I thought, oh wait, that's big.
Yeah. But it's the same business that underlies this time after time when you do examples. That underlies the fact that to have a wave at all, you've got to have a reduced wavelength, small compared to the radius of curvature of the background space-time, and that very fact is a key element in seeing that these interactions are unimportant. Okay. Other questions? Okay. So the kind of a medium that would be the best interactor for gravitational waves is a medium. Well, let me back up. Let me motivate this in the following way. There's a reciprocity relation in the theory of emission and absorption of gravitational waves that holds for any kind of radiation. It can be derived quantum mechanically using what are called Einstein A and B coefficients, but it has a classical version. And what it basically says is that there is an intimate relationship between the cross-section for a entity to absorb gravitational waves and its ability to emit gravitational waves. And if you have something that's a very good emitter, then it'll be a very good absorber, and vice versa. Now, we also know, or I have asserted, and we will see this as we start really looking at gravitational wave sources in detail, that the best emitters are things that are very compact masses that are close to their Schwarzschild radii, which means things like neutron stars and black holes. Things that are highly relativistic. They emit most strongly, and therefore they are the best kinds of absorbers. And so what I want to imagine is a universe that is filled with identical neutron stars. I could use black holes, but it's easier to think in terms of neutron stars because I can think in ordinary Newtonian language in order of magnitude. So I have a universe filled with neutron stars and nothing else. And they're all identical neutron stars for simplicity. And I want to look at the interaction of gravitational waves as they go by through this universe, interacting with this cloud of neutron stars. Okay. Now, what I'm actually going to do is look at the dispersion. I'm not going to look at the absorption, but the dispersion, if the absorption is strong, it will turn out that the dispersion is also strong. Dispersion is the easiest thing for me to calculate. And so I want to look at the dispersion beginning with the wave equation, but written in a form, well, no, I'm going to derive a version of the wave equation that I'm going to use. Let's recall that if I have a single neutron star, it emits gravitational waves in a manner such that the emitted waves, the neutron star is oscillating. It's undergoing quadrupolar oscillations. And then the HJK transverse traceless that's emitted is equal to 2 times, take the second moment of the mass distribution, or equally well the quadrupole moment, take its second time derivative and evaluate it at the retarded time and divide by r. So this is the formula that we derived before in the quadrupole moment approximation for the waves emitted by a single neutron star. Now, I'm going to be interested in the case where the oscillating quadrupole moment is present. It's oscillating because it's being driven by passing gravitational waves. And so that's going to be the origin of this time oscillating second time derivative of the quadrupole moment, or second time derivative of the second moment of the mass distribution. It's going to be caused by passing gravitational waves, but I don't need to know that just yet. I just know that this is the case. And I can turn that into a wave equation just by inverting the Green's function, the familiar Green's function. I can basically turn that into a wave equation that says box HJK transverse traceless is equal to IJK, this should be transverse traceless, times delta of, this is evaluated at t and x, delta of x minus the location of this neutron star. Now is that right? Let me just look dimensionally to be sure I've got it right. The delta function has dimensions of 1 over length cubed. This has dimensions of a quadrupole moment, which is length cubed over length squared. So that's 1 over length squared, and a wave operator has dimensions of 1 over length squared. So this is dimensionally right. And then there's probably a factor of 8 pi in here, because we know the Green's function involves a 4 pi, and I've got to get a 2 in the end. So I assert, so I'm just asserting, knowing about how Green's functions that would underlie this solution, that we can write the wave equation in that form. So you have a source located at the location of the neutron star. It's oscillating away, and as it oscillates away, it produces gravitational waves, and this is the solution of the gravitational waves produced by that wave equation. So I went from the solution back to the wave equation. You usually go from the wave equation to the solution. Okay. I did that because when the original wave equation from which we got this solution, it treated the internal structure of the neutron star. And I now wanted to use a wave equation now where I'm just regarding the neutron star as a tiny point source that's radiating in the same way as the neutron star with its true internal structure radiates. Now, if this is the emission from a single neutron star, and if instead I have a cloud of neutron stars with mean number density, that's the number of neutron stars per unit volume, n, so that the mean separation between the neutron stars is 1 over n to the 1/3. Then I just want to add up all of these contributions from the individual neutron stars, and then I can just smear it out, average it over a region that is big compared to the size of the interneutron star distance. And instead of writing this in terms of a sum over delta functions, just write it in a smeared out way as the box HJK transverse traceless is equal to ijk, second time derivative transverse traceless, times the number density of neutron stars. So all that's happened is this delta function that has units of 1 over length cubed has been turned into a number density of neutron stars in order to get the result of adding up over all the neutron stars in some region. So this is sort of a trick to go from a bunch of discrete sources to a smeared out source. But it's a trick that you would find also done in electromagnetic theory. Okay. So this is the wave equation that I want to work with. The next thing that I need to know is what is the this ijk second time derivative. Well, for each neutron star, ijk itself is the integral of rho xj xk d3x. It's the second time derivative of the quadrupole moment. Now I just want a rough order of magnitude version of the right-hand side. I don't want to do this with great care. Doing it with great care, I would have to look at normal modes of oscillation of the neutron star and focus on a sum over normal modes, and it can become complicated but perfectly doable. Well, I want to think of this neutron star as being excited in one normal mode by the gravitational wave force, which is causing the neutron star to undergo quadrupole oscillations in the transverse plane as the gravitational wave passes. And if I do that, then the perturbation in ijk caused by the passing gravitational wave is going to look like rho xj delta xk, that's the perturbation, plus xk delta xj d3x. And we know that these delta xj's are going to look like hjl transverse traceless with a 1/2 and an xl. So that's what they're going to look like. And so if you go through here and note that rho looks like the mass of the neutron star divided by its volume, and here this integration gives us a volume. And each of these x's is a size of the neutron star. I'll take the neutron star to have a radius r, has a mass m. So I'll replace each of these x's by an r. So I have an r here. Well, let's take an r here, an r there, and an h. So I basically have an m over a volume. I have an r, an h, an r, and a volume. And that whole thing then looks like m r squared hjk transverse traceless. Okay. With some coefficient, which I'll call alpha, that is of order unity, that just depends, in fact, on the details of the eigenfunctions of the normal modes of oscillation of the neutron star. So the second time derivative of ijk transverse traceless is going to be some alpha mr squared hjk transverse traceless. So I can feed that back into the wave equation, and once again I get on the right-hand side a term that is proportional to the gravitational wave field itself. Pardon?
You got the second time derivative on that.
Yes, I did. Thank you. Oh, just a second. Yes, absolutely. Okay. And so I now have a wave equation, box hjk transverse traceless, which is minus dt squared plus dz squared hjk transverse traceless is equal to alpha mr squared, again, two time derivatives, hjk transverse traceless. So that's the wave equation with, again, a source on the right-hand side that looks like just the quadrupole moment of the star itself, or the second moment of the mass distribution, coefficient of order unity, and a second time derivative of h, which is the thing that was driving the star to oscillate. We can now get ourselves a dispersion relation, just as I did previously, by assuming that these waves go as e to the I omega t, or e to the I kz minus omega t, just as I did before. And each of these time derivatives then becomes minus omega squared. So this becomes omega squared. That becomes minus k squared. This becomes a minus omega squared. And so I get a dispersion relation. I'm running out of time, so I will actually just write down that dispersion relation then, which if I just go through the mathematics, I wind up in the end, after doing some mathematics, after again making an approximation where a term is small compared to unity, which you can then check in the end to see that it's the case. You wind up with omega is equal to k, as before, times 1 minus 4 pi alpha n m r squared omega squared. I left out n for here, the number density of stars, okay, divided by, oops, I screwed up. An important point is that I'm deriving a normal mode of oscillation of the star. That normal mode has eigenfrequencies. That is, these waves that are making the star oscillate, they're driving it on or off of some eigenfrequency of oscillation, of quadrupolar oscillation. And so I'm going to assume that omega 0 is the eigenfrequency of oscillation, which is going to be something like 2 pi times 2,000 hertz, 2 kilohertz for a neutron star eigenfrequency. I'm going to assume that tau star is the damping time for internal oscillations due to internal friction. And that tau star will typically be of order seconds to minutes. And to know that that's the case, you have to know something about dissipation processes in neutron stars. So I'm just telling you, for quadrupolar oscillations, mass quadrupolar oscillations, these eigenfrequencies are seconds to minutes. Okay? So these oscillations have rather high quality factors. That is, they oscillate for a long time, but then die out due to internal dissipation, or due to dissipation due to re-radiating gravitational waves. That's another source of this tau star. And what that means is that instead of having a wave equation that has this form, you have delta I double dot transverse traceless plus omega naught squared delta I plus 2 omega, or 2 over tau star delta I with one time derivative is equal to the thing on the right hand side, alpha m r squared hjk tt. That is, you have the usual harmonic oscillator equation with a restoring force and a damping term, and on the right-hand side, the driving term. If you then feed this in onto the right-hand side of that equation, so this entire expression gets fed in onto the right-hand side in place of just the second time derivative. I want to feed in this entire expression. I then go through the analysis, and I get out a dispersion relation, which I will write down, omega naught squared minus omega squared minus 2I omega tau star. It's a standard kind of dispersion relation that you have for an oscillator that is driven off resonance. And then it is a straightforward calculation from here, using the same kinds of order of magnitude arguments that I used before, to discover that the attenuation length due to tau star is very long compared to the radius of curvature of space-time produced by these stars. And the amount of lag of a wave packet in going over this distance of the radius of curvature of space-time, again, is small compared to a wavelength. Unless the waves are right on resonance with the neutron stars, and the neutron stars are packed side by side with almost no space in between them, in that case, you can get a small amount of dispersion by a few times the wavelength lag in going over the distance r, and you can get some moderate amount of attenuation if you're right on resonance and the neutron stars are packed side by side. So the details will be in some reading and perhaps in an exercise that I'll give to you. But this is a sketch of this example. So all of our examples, one after another, show that under any circumstances, any plausible circumstance in our universe, absorption, dispersion are totally negligible. Similarly, scattering is negligible and unimportant. And we just don't need to worry about them. Okay, thanks. And so, and let me remind you again that I would like to meet with anybody who wants to meet in the lounge in Bridge Annex at about 10 minutes past 4 today for discussion of the course material.